Okay, so let's take a look at our last section, so 4.3. So past couple days we spent a lot of time on graphing, okay, looking at functions that have vertical, horizontal, slant, and even curved asymptotes. Now we're going to look at solving equations. So eventually we want to be able to solve something like that. That's a rational equation. Okay, we've got polynomials in the top and the bottom, and I'll show you how to solve. Okay, there's a process you go through, and once you know the process, it's the same process every time. So for equations, we're mostly going to focus on doing it algebraically. When we get to some inequalities, that we're going to do graphically. If we have time, maybe we'll look at an equation graphically, but we'll see. Can you just shut that for me? Thank you. All right, so we're going to look at a word problem to start off with, and it's going to end up being an equation that's rational. Okay? So the problem we're going to do involves distance, rate, and time. So first, I just want to make sure everyone knows that formula. Distance equals rate times time. Okay, other than giving you that formula as kind of the background, we're just going to jump right into the first example. There's nothing else I need to show you. Okay, so in this problem, Sue is trying to get somewhere, and she's going to do part of the journey by train, and she's going to do the other part by car. So it says she drove 30 miles to the train station, got on a train, and then she completed the trip from there. In all, she traveled 120 miles. We don't know how fast the train or the car is going, but what we do know is that the average rate of the train is 20 miles per hour faster than the average rate of the car. It doesn't tell us exactly how fast either one of them was going. We just know that one is faster than the other, and we know how much faster. Okay. Any questions so far, just on the information they're giving us? All right. So the question is going to be, or what they want you to do, is find an algebraic expression for the time that it takes to complete the trip as a function of x, which is going to represent the speed of the car. So we want to find an equation for the amount of time it takes to complete the trip as a function of how fast she goes in her car. All right, so when we're done, we'll have a formula that you can say, all right, she drove 50 miles per hour in the car. I can plug it in, and I can tell you how long it took to do the trip. Whole trip, car and train together. Okay, so let's figure out just kind of a big idea, like the concept first, and then we'll try to figure out variables and use a formula. So she's taking two modes of transportation. So she has the time it takes to drive in the car and the time it takes on the train. What would we do with both of those times to get the total time for the trip? Yep.
Add them together.
Yeah, so the total time is going to equal time in car plus time on train. Or I guess you could say in train. But you wouldn't say time on car. You say time in the car. So time in the car plus time on the train. So now we want to figure out how we write those out. So we'll call this t of x. Remember, x is how fast she's going in the car. So we're going to have times. We're going to have a time here. We're going to have a time here. If I rearrange my distance formula, distance equals rate times time, and I solve it for t, what would that look like? Yep. So we have distance equals rate times time, and she said t equals r. What did you say again? R divided by d.
No.
D divided by r. So that's what we're going to put in each of these boxes. D divided by r and D divided by r. So let's start with the car. What's the distance that she traveled in the car? 30 miles. So we traveled 30 miles in the car. What's the rate of the car? X. We don't know. Distance divided by rate, that's the time in the car. Right? Now let's do it for the train. What's the distance she traveled on the train? 90. Right? We're not given that, but she did 30 in the car. She did 120 altogether, so it must be 90 on the train. So distance on the train is 90 divided by the rate of the train. Yeah, it's 20 miles per hour faster than the car. So if the car is X, there's your equation that gives you the time of the trip as a function of how fast she drove in the car. And that's it. We're going to do some things with that, but any questions so far? Now, when we're trying to figure out different things, sometimes it's easier to have these as two separate fractions. Sometimes it's easier to combine them together with a common denominator. I'm going to leave it like that for now, but I think we are going to have to combine it depending on what they ask us to do next. Okay, but we've answered the question for this part. Okay, any other questions on that? Okay. So now we're going to look at that equation, 30 over x plus 90 over x plus 20, and I want to find asymptotes. I want to find roots. That's where it crosses the x-axis. The end behavior model. So that's where you need to combine this together to do the end behavior model. And then we're going to do a complete graph, not by hand, but on the calculator. Let's start with vertical asymptotes. This problem has two vertical asymptotes. Yeah?
0 and negative 20.
0 and negative 20. I'm not saying that they really mean anything in the context of the problem because x is a speed. And I don't think negative 20 makes sense, but I think 0 makes sense, right? As x gets closer and closer to 0, so as she drives slower and slower and slower, imagine she drove 0.0001 miles per hour. How long would it take for her to complete the trip? Like, roughly. If she drove 0.0001 miles per hour.
I don't know, a couple years.
Yeah, a long time. Yeah. So if you plug in 30 divided by 0.000001, what's going to happen is that's going to be a huge number. It's like it's going to go up to infinity. So the fact that we have an asymptote going to infinity at 0 makes sense. If she drove 0 miles per hour, it would take infinitely long to complete the trip. She'd never complete it. Right. The negative 20 though, there's no real world context for that number. But algebraically there is. So there's your vertical asymptotes. Let's do the horizontal asymptotes. But to get that, we need the EBM. All right. So to get the EBM, we want to combine these together. What's going to be my common denominator? What times what here? Yeah? X times x plus 20. So that means I need to multiply top and bottom of that fraction by the other denominator, and top and bottom of that fraction by the other denominator. Just kind of squeezing in the x plus 20. So that's distributive. 30x plus, what's 30 times 20? 600. Let's switch back here. So 30x plus 600 plus 90 times x. All right, and then in the bottom, it's just x times x plus 20. Let's do that out and then combine like terms. So 30x plus 90x gives me 120x plus 600 over x squared plus 20x. Okay. Now I can find the end behavior model. What's the highest degree term in the top?
120x.
120x. Highest degree term in the bottom?
X squared.
Squared. And when I reduce that, what am I left with?
120 over x.
120 over x. Yeah. Okay, so there's your NEDM. Now we can find the horizontal asymptote. So if you let x get bigger and bigger and bigger, what does that fraction approach? 0. And it should, because as she drives faster and faster and faster, the time to complete the trip approaches 0. But it can never reach 0 because she still has to travel from point A to point B. No matter how fast you go, it's going to take some amount of time. It's not instantaneous to get from point A to point B, unless you travel infinitely fast. That's weird. So you've got horizontal asymptote, vertical asymptote, end behavior model. What else? Complete graph, I'm going to do that in a second. Oh, the roots. So the roots are where you cross the x-axis. If you pick any coordinate on the x-axis, what do they all have in common? Every single coordinate on the x-axis. Yep. The y equals 0. All right. So if you're trying to find where you cross the x-axis, let y equal 0. So easiest one to look at, I think, is writing it like this. Right? That's equal to y, or f of x, or t of x, whatever you call it. That's y. So if we make that 0, you're now saying that a fraction equals 0. How can a fraction equal 0? What would have to happen?
If the top equals 0.
If the top equals 0. All right. So to find my zeros, set the top equal to 0. And that'll tell you where the fraction equals 0, which tells you where you cross the x-axis. So I'm going to get 120x there we go, equals negative 600 divided by 120. And where do I cross the x-axis? Yeah, negative 5. Again, does that really have a point in the real world context of the problem? Not really, because negative 5, you can't travel negative 5 speed. But algebraically, that's what it is. Okay, so we got our zeros, our asymptotes, our model. Last thing is to graph it. Now, when they ask for a complete graph, there's two things. One, I could find a complete graph of the actual word problem, which means negative x's wouldn't make sense, things like that. Or I can actually find a complete graph of this whole thing, like algebraically, saying, you know what, x can be negative. It can be anything we want, even though we know x should be positive. So I'll do it both ways. Let's start with 30 over x plus 90 divided by x plus 20. Okay, and I would put in the parentheses just like that. I'm going to go back and look. So I'm going to go at least to negative 30 on my x-axis. That'll cover the root as well. Let's go negative 30 to 30. Try that. So negative 30 to 30. Horizontal asymptote is at 0, which is included with negative 10 to 10. So let's just try it like that. All right, so I can see, if I went further to the right, I could probably see it better, but I can see the time it takes to complete the trip is starting to go down more and more the faster she goes. The negative part of the graph doesn't really make sense for the word problem. Right? But I can see, if I zoomed out more, I could probably see that there's a vertical asymptote right there. Let's set the y max to 40, just to see if it looks like that line is going almost straight up. Yeah. So it's hitting an asymptote right there. Okay. And it crosses the x-axis at -5, which is, I think, what we said. Yeah. So there's a nice complete graph of the whole thing. If you wanted just a complete graph of the word problem, just go like this. Set her minimum speed at 0. Maximum speed, well, could be however fast she's driving. But the faster she drives, the less and less time it's going to take to complete the trip. Notice, though, at a point, it doesn't really make a huge difference. At first it does, but once she hits like, I'm just going to guess, even way before that. So once she hits like somewhere around 10 miles an hour, it doesn't really matter if she drives 10 or she drives 30, because, I mean, it's going to take off a little bit of time, but it's already dropped way down. So driving a little bit faster isn't really going to make a difference, a big difference. Okay. All right, so there's our complete graph. Now what do they want us to do? It says Sue has 2 hours to complete the trip. Find the speed that she has to travel by car. Do it algebraically and graphically. Okay, let's do it algebraically first. So she has 2 hours to complete the trip. Is 2 hours an x value or a y value? Yeah. It's a y value. X is how fast she drives, y is how long it takes to complete the trip. So let's just plug 2 in for y and then solve. So 120x. I think it's easier to use the combined one rather than the one with the separate fractions. X squared plus 20x equals 2. All right, now what I would do first is I would multiply both sides by the denominator. Now we have to be careful when we do that, because when you multiply both sides by anything with a letter, you can introduce extra answers into the problem. Answers that are not part of the original. So what that means is when we're done, we have to check our answer. All right. As long as we check it, that's okay. So we get 120x plus 600 equals, and now multiply both sides by x squared plus 20x. So it'll cancel on the left, and on the right, we get that. Once we get that equal to 0, what kind of equation do I basically have there to solve? See, how about Kate? You see what kind of equation we've got?
Quadratic.
Yeah, it's just a quadratic. So maybe it'll factor. Maybe we use quadratic formula. But once we're done, that's all we have to do. So let's get it equal to 0. And can anyone tell me what would be on the right-hand side if I get that equal to 0? Emma?
2x squared minus 80x minus 600.
Minus 80x. And then what did you say the last one was?
Minus 600.
Minus 600, yep. Now, what I could do here is I could divide everything by 2. Just makes everything a little smaller. And now, let's see, is that factorable? 2 numbers that multiply to give me 300. And add or subtract to give me 40. You want to think of 2 numbers that multiply to give you 300 and add or subtract to give you 40. Yeah. Justin?
Negative 30 and 10.
30 and 10. Yeah, I think that might work. Let's try it. So 0 equals, we got x and x, negative 30. You said negative 30 and what?
10. Yeah.
10? Positive or negative?
Well, that would be negative to add to 40x.
It'd have to be negative to add to 40x, but what would it have to be to multiply to give you a negative here?
Positive.
It'd have to be positive. So yeah, I'm not sure that's going to work. Unless we made a mistake with our signs and one of those is supposed to be positive, but I don't think we did. All right, so I'm not seeing a quick way to factor that. Is anyone else seeing a factor it? So what I'm going to do is just we can do quadratic formula because I don't see a way to do it quickly. All right, so we have negative b plus or minus the square root of b squared.
Negative 40 squared.
What's that?
Negative 40 squared.
Yeah, I was gonna show people how to do it, but I'll just do it then. Plus or minus the square root of 1600, so it's just 40 times 40. B squared minus 4ac all over 2. All right, what's going to happen here? You've got minus a minus, so that becomes a plus. What's 4 times 300 is how much? 1200, and 1200 plus 1600? Yep, 2800. Okay, so let's do that out and see what her speed comes out to. Yeah, the square root of 2800 is not a nice number, so there's no way we would have factored that. So that's the square root of 2800 plus 40 divided by 2. Yeah, we wouldn't have got that. So it's 46.46 miles per hour. And that was x, which is the speed of the car. Now, there is another answer we can look at. We can do 40 minus the square root of 2800. But that's the square root of 2800. It's 52.9. Should I do 40 minus 52.9 divided by 2? Why not? Yeah, it works algebraically, but it doesn't make sense in the problem. So don't worry about the negative answer. But the other thing we do need is the speed of the train. So what's the speed of the train if the car is going 46.46?
66.
Yeah, said it was 20 faster. So algebraically, that's how you do it. You end up having to solve a quadratic equation. It doesn't factor, but it's not the end of the world. We just use our calculator and see what we got. So that's algebraically. Graphically, I would take and put a line at 2. And what do you think Yeah, I'm going to go a little further. Although I already know I'm far enough. If I hadn't already solved the problem, I might not think I was far enough to see the intersection. So how do we get the intersection? What do I do for that? So, Ashley?
Wouldn't you do like the second calc
Yep. Second calc,
and 5?
and then 5. So pick a point on the blue, the red, do your guess, and you get 46.46. Right, so there's your answer graphically. Any questions on that? Okay, we know there's another answer off the screen, okay, but we're not going to really worry about it because it doesn't apply to the problem. Right, so that's an example. We just solved a rational equation because we had variables in the top and in the bottom. Okay. It's a rational equation. All right, so since we multiplied both sides by I think it was what, x squared plus 2x or something like that. Whenever you multiply both sides by a variable, you can end up with what's called extraneous solutions. What that means is you didn't do anything wrong. Because you multiplied both sides by a variable, you created what could be an extra answer that doesn't actually work in the original problem. So the only way around that is to check your answers. Okay, so check your answers. And I'm going to show you an example of doing that with a very simple equation. Okay? Not even a rational one, just a basic algebra 1 equation. I'm going to do something to it that creates an extra answer that doesn't work. Okay, and it'll be obvious that it doesn't work in the original problem because it's a very simple equation. But when we get into more complicated equations, it's not obvious that it wouldn't work. You're going to have to check it. So let's look at that equation, x minus 1 equals 0. Before I do anything, can someone tell me just what the answer to that would be? X minus 1 equals 0? 1. Does anyone think that there is another answer besides 1? No. So we all agree the only answer to this problem is 1. All right, let's do something to it. Let's multiply both sides by something with a variable. Let's multiply both sides of this equation by x. So you get x squared minus x equals 0. My first question is, if you plug 1 into that new equation, do you still get 0?
Yeah.
Yeah. So the original answer still works. We didn't mess that up. But now there's another number you could plug in. Does anyone see the other number you could plug in for x and get 0? Yeah? -1. If you plug in -1, you would get 1 minus minus 1. So you wouldn't get 0. So not -1, but a good guess. Yeah. 0. If you plug in 0, 0 squared is 0. 0 minus 0 is 0. So now this equation has two answers, 0 and 1. Let's check, is 0 a solution to the original problem we had? No, we all agreed that 1 was the only answer, 0 was not. So by multiplying both sides by a variable, I created an extra answer that doesn't work. Okay? So check your answer. Questions on that? All right. So basically, the way we do this is we try to eliminate the fractions. Okay, just like we did in the distance problem. You're going to multiply everything by the LCD. So we have a denominator of x minus 1. We have a denominator of x minus 3. And a denominator of x squared minus 4x plus 3. Now I want you to kind of notice something. If you multiply the two denominators I have in parentheses together, what do you get? Yeah.
That x squared minus 4.
Yeah, you get the other denominator. There's no reason that always has to happen. I could change one of these numbers and make it so it doesn't happen. But if I do that, it's going to make it a lot harder for you to solve it. So anytime we have a problem like this, these two denominators will always multiply together to give you the one on the other side. That makes it a little easier to get the LCD. Right, so what we're really going to do here is multiply everything by the common denominator, which is x minus 1, x minus 3. That's your common denominator. So you're going to multiply this by x minus 1, x minus 3, this, and this. We're going to get rid of the fractions by multiplying everything by the least common denominator. It's kind of like if I showed you something with numbers, 2 over 3 plus 7 over 5 equals 12 over 15. Well, if you multiply everything there by 3 times 5, 3 times 5, 3 times 5, and 3 times 5, you're going to get a lot of nice things that cancel. Your 3's cancel there, your 5's cancel there, and the whole thing cancels there. So you'd have to have a variable in there somewhere to make this work. All right. So now all you're left with is 10 plus 21 equals 12x. That's a much easier equation to solve than when you have all those fractions. Okay. So pretty much exactly the same thing is going to happen here. Multiply each term by the product of the denominators. And what cancels out in the first fraction? Yeah?
X minus 1.
X minus 1. What cancels out in the second fraction?
X minus 3.
X minus 3. And in the third fraction? Yeah? All of it. Because x minus 1 times x minus 3 is what's in the bottom. So all you're going to be left with now, and you're going to be careful because this is a distributive, is 2x squared minus 6x. And now you distribute this. I circled it like that because if that was a minus in between the fractions, that would be a minus 1 distributed to everything. In this case, it's a plus 1. So now distribute plus 1 and nothing really happens. So it's just 1x, which you can just write as x, and then positive 1 times negative 1 is negative 1. And now we just have a quadratic to solve, just like before. That's what usually happens on these problems. They usually end up being quadratics. Maybe not always, but a lot of times. It won't be anything higher than a quadratic. Okay, so we've got 2x squared. What's minus 6x plus x? Negative 5x. And let's get it equal to 0. So what would my constant be? Yeah, negative 3. Okay, let's try to factor it. Maybe we'll get lucky. If not, then we're going to use quadratic formula. Yeah?
X minus 3 and then 2x plus 1.
All right, let's try it. So you said x minus 3 and 2x plus 1. So we get 2x squared, that's good, plus x minus 5, plus x minus 6x. Well, plus 1 minus 6 is minus 5, and negative 3 times 1 gives me negative 3. Perfect. So what value of x would make the first factor 0? 3. What value of x would make the second factor 0? Negative 0.5 or negative a half. Now, at this point, there's 3 things that could happen. Both of these answers work. One of them works, one of them doesn't. Or they both don't work. So we have to plug them back in and check them. Let's start with 3. So I did the original problem in black so you can see what it was. What happens if you plug 3 in for x in the original problem? Yeah?
It doesn't work because you don't get 2.
Why not? What do I get?
Because 3 times 2 is 6.
So in this part, I would get 6 over 2. So that's 3 plus, what about the next part? Yeah?
You get 1 over 0.
I get 1 divided by 0. So I get 3 plus undefined, which is definitely not what's on the other side. So you cannot plug 3 back in because it would cause you to divide by 0. So you need to cross that answer out. that is extraneous. It's an extra answer that we made, not because we did something wrong, but because we multiplied by a variable. Now let's check negative a half. That, you know what, we don't even need to check it really. As long as you can plug it in and you don't divide by 0, then it would work. Right? I'll check it this time just to show you, but that's kind of the quick way. If you plug it in and you don't get 0 in the denominator, it's good. All right, but if you plug in negative a half, you get 2 times negative a half is negative 1. Negative a half minus 1 is negative 1.5. Negatives cancel. Plus 1 over, what's negative a half minus 3? Negative 3.5. So 1 over negative 3.5. And I'll check what that comes out to. I guess I can check it right now. So it's 1 divided, well, not here. 1 divided by 1.5. All right. Plus 1 divided by negative 3.5. Okay, so when you plug in negative a half on the left, you get 0.3809. So we'll see if that's what we get on the right. So we get 2 divided by negative a half squared. That's a quarter. What's negative 4 times negative a half? 2. 1/4 plus 2 plus 3. So that's 5.25. So 2 divided by 5.25. Hopefully I did all my math right because I just kind of did some of it in my head. But yeah, I get the same thing on the left and on the right, so the answer works. Okay. All right. If you forget to cross out that one that doesn't work, you'd lose 1 point for that. Okay, you got to make sure you cross it out if it doesn't work. Okay, let's look at this one. So, a little different because this time they already have it equal to 0. So it's like it's ready to go when we get it into a quadratic. We're not going to have to bring anything to the other side. Yeah. Can you? Yeah, just what am I going to multiply all my terms by here? Yeah. The least common denominator, which would be x squared plus 2x, and I'm just going to think of it as factored out. I'm going to think of it as x plus 2, or x times x plus 2. So you're going to multiply this by x plus 2, this by the least common denominator, and this. You can do it on the other side too, but it's 0, so it doesn't really matter. Okay. What's going to cancel in the first fraction? X. What cancels in the second fraction? X plus 2. And in the third fraction? All of this denominator with that. So the first thing we have to do is we have to FOIL out x minus 3 to do all that out. So we're going to get x squared plus 2x minus 3x. So minus x minus 6. Next part, well, it's pretty straightforward. It's just 3 times x. And what's the only thing left in the third fraction? Just the 6. So it's already equal to 0. So now we just combine like terms. See if we can factor it. If not, quadratic formula. So x squared. So that. Negative x plus 3x is 2x. And negative 6 plus 6, what happens there? They cancel. So now to solve this, I can just factor out the GCF. What would make the first factor 0? 0. What would make the second factor 0? negative 2. Right, let's see if we can plug 0 in and see if it works. Can we plug 0 into the original? No, you'd be dividing by 0 right there. So you can't use that answer. Let's try negative 2. Can you plug negative 2 into the original? No, you'd be dividing by 0 right there. So this problem has no solution. It's impossible. Right? Which means if you were to graph what's on the left, it would never hit 0. Never hit 0. Any question on that one? So we looked at one that had a no solution. We looked at one where one answer worked and one answer didn't. We didn't look at a case where they both work, but it's the same thing. So it says using example 1, so that was the train problem. What possible rates could Sue travel to make sure she completes the trip in less than 2.5 hours? So if I want to do that graphically, what would I have to do here? I've already got the original problem in y1. What would I want to put in y2? Yeah.
2.5.
Yeah, we're going to put in 2.5. All right. And now that I did that, what would I want to do now? Click. Okay, I'll see where they cross. All right, so they cross at 34.88. So, okay, now what would I do?
It's like anything that's so then anything that's like greater than
Yeah, anything that's greater than. Can it be equal to 34.88? No, if it was equal to 34.88, she would complete the trip in exactly 2.5 hours. So this is strictly less than. So at what possible rates? So Sue needs to travel at, or I'll just say needs to travel greater than 34.88 miles per hour. So Sue needs to travel at a speed greater than 34.88 miles per hour. What kind of problem is that? When I have greater than in there, it's not an equation anymore. What is it? Yeah,
It's an inequality.
it's an inequality. So the last part we're getting into is inequalities. And the idea is you still graph it on the calculator. Just remember your answer is not where it equals an intersection. It's usually greater than the intersection, or equal, or it can be less than or equal. But it's not just equal. Okay, remember we can always have hidden behavior. So there might be things that happen off the screen. And when you're dealing with problems that aren't word problems, any x value goes, right? Positives, negatives, fractions. So you've got to make sure you look everywhere when you're not dealing with word problems. Okay, if we were solving algebraically, maybe we'll look at one, we'll see. We can make a sign chart. Okay, that's something we've done before where we see where something's positive and then where something's negative. In fact, it's exactly, we've already done that. It's where we usually make a number line and the signs alternate positive, negative. People remember kind of doing that? Yeah. So that's how we could do it algebraically. All right, so let's try this one. this one can be done algebraically or graphically. The problem is if you want to do it algebraically, you have to get everything on one side and get it 0 on the other. So I think for this one, I'm just going to do it graphically. So we'll put what's on the left in y1, put what's on the right in y2, and look at where what's on the left is below what's on the right. Okay. So let's see what happens. So we've got 2x squared plus 6x minus 8, and then divide by 2x squared plus 5x minus 3. And put in a line at 1. Okay, so we're going to look where the graph in blue is below the graph in red. It's not a good window. So I'm going to start with a standard window and go from there. All right, so it looks like that line in red is a horizontal asymptote. So in this middle section, okay, it's above. So that's not really what we're interested in. Okay. We're interested in trying to describe, let's put this here. This section looks like it's definitely below what's in red. And I think it's in that section too. I can double check it just by going to the table. And let's plug in 3 and see if the blue number, yeah, it looks like they're equal, but the blue number is still smaller than the red. If you go to 5, it looks like they're the same. But I'm guessing what's happening is we're running out of decimal places, so they get very close very quickly. But the blue one is always less than the red one, even though it's going to round it off and say it's not. All right. So where is the blue one below? Well, you can head to the left forever. It's always going to be below there. Up to some value. Okay. I'm just guessing, but it kind of looks like the vertical asymptote is at -3. Yep. So we have an error. So your vertical asymptote is at -3. So from -infinity up to -3, that describes this section right there. Okay, and now the other vertical asymptote, I don't know, to me it looks like it's right about there. Just guessing. Looks like it's right in between 0 and 1. If you're having to look at a graph, they're not going to make it hard to figure out the asymptote. It's going to be something you can tell easily. So I think it's 0.5. It is. All right. So the second part of the graph is from 0.5 to infinity. That's where the graph in blue is under the graph in red. Okay, just don't go anywhere between -3.5, because then the graph in blue is above the graph in red in that section. Okay. So, any question on that one? Not really too much algebra there. You're just using the graph. Did that one? This is another solve graphically. Got a little under 15 minutes, so we'll just do it. Maybe something weird happens. I don't remember. Let's try it. Where am I going to get a vertical asymptote before I even graph anything? Yeah, at 2. Okay, we're going to get a vertical asymptote at 2. That doesn't really tell us a lot, but that's all we know so far. So x to the 4th minus 3x cubed plus 2x squared. I'm going to make sure you come back down from the exponent. Plus 2x squared plus 2. Okay, divided by x minus 2. And we want to know where we are above 15. So I'm going to have to set my y max a little higher, I think. Let's go up to, I don't know, 25? Let's hit graph. Okay, so we'll be a little careful here. So we want to know where that graph is above 15. Well, if you look at the graph in blue, is the bottom section ever above the red line? No. So you don't really have to worry about that at all. How about the top section? Is that ever above the red line? Yeah. In how many areas is it above the red line? 2. From here to here, and then from here to here. Here it's not. So you got to be a little careful how you write that. So we're going to have 2 intervals. And the lower bound on this first interval is going to be right there. Where did I just put a vertical line? At 2. So the graph in blue will be above the graph in red from 2. Can I include 2 or not include 2? I can include it? So if I plug it in for x, I'll be okay? No. It would cause me to divide by 0. So I can't actually use 2. But I'm going to go from 2 up to right there. I just need to see where they cross. Second calc, intersect. I just keep pressing right. Someday I'll get over here. The guess does matter because they cross in 2 spots. Just put the guess close to what you think it is. It's 2.22. Did anyone notice if the screen gets brighter and darker? Or maybe it's just me from the side. No? It's definitely me then. Okay. So from 2, yeah, look at it from the side. It's dark. So from 2 to 2.22. Now, I should be careful. Can I be equal to 15 or do I have to be greater than 15? I can equal it. So that's okay. Or second calc intersect. There's another intersection over here. That's from 2.68 going on forever. 2.68, I can include it because of that right there. And then when I go to infinity, well, I can never reach it, so don't put a bracket on infinity. Okay. So that describes this section and that section. So it's a small section that's not part of it that you got to be careful between 2.22 and 2.68. You got to exclude that. But everything else is okay. Any questions on that one? Okay. All right, so the homework tonight. So it's the take home. Okay, it will be due for you guys at, class starts at what, 10:39?
Maybe start at 9:13.
Oh yeah, so, wait, so tomorrow I have you guys third period, so 8:30, 9:15. So it's due when you come in, which is right around 9:20. If you're in period 7-8 and you're watching this, it's due at 10:05. If it's late, that's E0. Okay, so you have to get it in. Please email it to me if you're absent. Take a picture of it, send it somehow. Any questions on that? Okay, second part will be in class tomorrow.